looks the same as behavior, but okay. So in our packets, we're going to be working with problems as well as this kinetic molecular theory packet. So if you could make sure you have both out. And I greeted you, yes, with this on your desk. Okay. Yesterday, we reminded ourselves, good morning, sir, of STP, remembering that molar volume can be applied at that. Now, of course, we realize this is only with gases. We would never say this is the volume of a solid at STP and so on. So whenever you read STP within a problem, our brain needs to remember the conditions, but also that we can apply this. Sometimes, instead of saying at STP conditions, you're given those temperatures and pressures. So we just need to be able to recognize those. When we are working with gas law problems, we are always in Kelvin. Always, always, always. Primarily, thermometers and temperature probes measure to the 10th. And so usually that will be the position of our degrees Celsius. But we do want to add 273.15. We'll probably be employing the even odd rule. If you need a reminder of that, just let me know. Just a reminder of common units. Now, we ended class yesterday talking about a barometer. So I just wanted to actually show you. Yeah, but okay, this is the up close of the little tray, if you will, or vessel that contains liquid mercury. And then that at least meter high glass tube that contains the mercury. You measure the height of mercury. Fair weather at sea level is approximately 760 millimeters of mercury. That would be the height. That is equivalent to what we call 1 atmosphere. So those of you that got in the garbage bag and experienced the bear hug of atmospheric pressure, that is approximately 1 atmosphere. At sea level, and we're a little above, but close enough, that is what we can say we experience. Kilopascals is another unit not used very often. So because so often we're referencing atmospheric pressure as we proceed through the chapter, that's what we measure at gas pressure with, but often we need it to be an ATM for different problem solving. So that probably is the relationship we'll need to depend on from this sheet. I will give this to us. You don't have to memorize this. With the kinetic molecular theory, we saw that the temperature of the gas is directly proportional to the kinetic energy. It doesn't give us the value, but it's comparable. So if we know two gases are at different temperatures, whichever has the higher kinetic energy. If they're at the same temperature, they'll have the same kinetic energy. The gas laws. You never have to know them by title. The relationship of pressure and volume, relationship of volume and temperature, pressure and temperature, and then all three. In our packet, the kinetic molecular theory packet, but also in the unit packet, we need to understand the relationship between the variables. So we talked about pressure, volume, amount, and temperature. If you change temperature, well, that can change pressure and volume. If you change volume, that can change pressure and possibly temperature. So we just understand that if we're looking at the relationship of just, for example, pressure and volume, then amount and temperature are being kept constant, just to remember. But we said last Friday, these are inversely related. When you increase volume, pressure goes down. However, if we're just looking at volume and temperature, if you increase temperature, your volume should go up, and so on. This is the mathematical relationship, yes? Okay, so what I'm going to ask is we build on this by, okay, in your unit packet, we have this kind of summary of our unit, but then, so depending upon the copier that copied your packet, this was to be page A. Ducks. It doesn't come through very well. So this begins page A. What I'd like us to do are these problems, and I suggest this order. They'll kind of build a little on each other, or these are kind of related and these are kind of related. You'll need our calculator, and you may need to rely on this given information. In addition to these, I'd like you, so this kinetic molecular theory packet, we do have the numbering of the pages in the bottom left. So I told you these are called we do, you do. Wait, I do, you do, we do. But anyway, on page 4, I'm asking us to do the first you do, A through D. And then on page 5, we're referencing this, God bless you, A through D. You can fly solo, you can work with a partner. I encourage you, go to your lab benches. Do you want to stand to do this problem solving? And I have the answers, of course. So if you want to be checking yourself as you're going, check in with each other. But no matter what, at the end, we'll make sure we're all good. So I would think let's see where we are in 15 minutes. Okay? I am here to address any concerns. What questions do you have? Good? All right. Go team. So here are the answers. God bless you. You didn't have to drop it. All right, so I'll just go in order on these A, B, C, D. All right, 3D. Could you do 4? Yeah, 4D, 6B, 7D, 8D, 10D, 18B, 19D, 20C, 21B, 23C, 24C. Yes. Oh my gosh. I did it backwards. It was late at night. No, no excuse. No excuse, Gearhart. You're so right. No, I needed E. Thank you. Thank you. Oh my gosh, not even. I don't know why yeah. So we'll learn. It's called root mean square velocity, but it's the speed of your gas determined by temperature and molar mass. And they're telling you they're all at the same temperature. So then just molar mass plays a role. The heavier, the lower the speed, the slower. Yeah, so this would be the slowest, and then this would be the quote unquote fastest. Yes. Absolutely. Did we remember? Is that clear? Oh, that's not good at all. So I like to rearrange my equation and then plug in. So 6.35 liters times 0.892 ATM times 293.2 Kelvin divided by 328 Kelvin times 1.05 ATM. And we get 4.82 liters. Do you need more than that, Matthew? Okay, yes, ma'am. The overwhelming majority of the time, the sig fig rule is lowest, right? Because we're multiplying and dividing most often. But to convert to Kelvin, we add. And when we add, it's number of decimal places. Yeah. So, yeah, that's why. So we can only report to the one place, hence the 328. But this to the 10th. And so we end up getting 293.15. Even odd rule, when we report the 10th with a 5 with nothing else after it, we look, odd becomes even. I'm so glad you asked that because we needed a reminder. Any questions on those, or what questions do we have, I should say? Yes. C. Absolutely. Absolutely. I'm so glad that because I was going to address this no matter. Okay, so what they're saying is, okay, first off, ideal gas. When you are told you have an ideal gas, that just gives you permission to use any of our gas laws. Any of our gas laws. That's all. Okay. So you're at 27 degrees Celsius and 1 atm pressure. By what factor will the volume change if the gas is heated to 127? So I'm just asked about volume and temperature. So pressure must be kept constant. So my brain goes to, I know they're directly related. V1 over T1 equals V2 over T2. You don't have to memorize these. I will give the equations. I'll tell you a handy way though. My physics teacher in high school would say, the vegetables sit on the table. The vegetables and potatoes sit on the table, but isn't a vegetable potato. But anyway, just a reminder. Now, they're asking, what factor will the volume change? Okay, well, 27 degrees Celsius, well, that would be 300 Kelvin, and I'm changing it to 400 Kelvin. They're asking how the volume changes. Okay, so I want to know, how does V2 compare to V1? Yeah. So are we okay if I just rearrange the equation? Because I want to know, what factor does it change? How does V2 compare to V1? After we have increased temperature here by 100. Well, look at that, 4/3. Now we can check ourselves. I wonder if maybe we chose B. But if V2 is 3/4 of V1, then it's going to be a smaller volume. And we know when we increase temperature, volume goes up. So that's a way we could check ourselves. Bryce, you asked about that. Does that? Okay. Other concerns? And we can totally flip this, right? I mean, if it feels more comfortable, we could say T1 over V1 equals T2 over V2, as long as what you do to one side of the equation, you do to the other. Yeah, totally allowed to do that. We cross multiply, whatever you need. Okay, so particulate diagrams, don't we love them? So they are giving you this as a comparison. So I just tried to gather as much as I could. Okay, it's a 1 liter vessel. I have hydrogen. That's why hydrogen is diatomic. That's why it's showing those two spheres touching at 200 Kelvin. Yes. No, that's what I was just going to reference. So thank you. Yeah. I drew these to be able to get those. And I left those. I'm so sorry. No, totally fine. As long as they look different, and neon is not diatomic. So those should be single spheres. You don't have to know the neon is a little bigger than diatomic hydrogen, just as long as it's a single sphere. You could color it in, whatever, but definitely shorter arrows. Yeah. Questions? Are we getting better and better? Particulate diagrams. All right. Then Maxwell-Boltzmann distribution. Okay. Now, you're not told the amount of change, So your curves do not have to look exactly like mine. For the first change, you need to make sure that the average, where the peak hits, is right to the original. And we know the greater the average, the greater the distribution. So it should be lower and broader. And then here, this should be higher because a lower temperature, a lower speed, still same amount, but we're not going to have as broad. So have you learned in calc how to find the area beneath a curve? Okay. So it doesn't say at all that you have a different quantity. Oh, forgive me. A higher molar mass at the same temperature. Okay. So same temperature. How does that affect speed? Well, they're both at the same temperature. So it's not that one is higher than the other. But this has a higher molar mass. The greater the molar mass, the lower the speed. Yeah. So if it's a lower speed than this average, and I'm moving forward with the assumption that they're the same amount of gas, so I have to show the same amount, but I know with the lower value, it won't be as broad. You don't have the variety. Does that make sense? So is that okay? You're sure? Okay. And so this, you just have to be the final one, more to the right, the peak, and broader. Any questions? Any clarity that I can provide? All right. We're going to talk about those next. So we'll put this to the side for just a moment, or for a little bit. All right. I don't know if maybe in some of your math and science classes or even English classes, you've been given papers that have this NIMSY designation? I'm not sure. NIMSY stuff is good. So this is the National Math and Science Initiative. Years ago, Peters Township partnered with them, and they embedded a lot of resources for us in math, science, and English AP courses. So anyway, they are quality stuff. So I just kind of harvested what is worth taking a look at. So we said, like, what can we measure about a gas? These things, yeah. Okay, gas pressure. Here would be Boyle's law, yes. You don't have to know, and you don't have to memorize. Oh my gosh. You don't have to know it's called Boyle's law. We just have to know the relationship of pressure and volume, and if we graphed it. So this is showing pressure versus volume, what it would look like. Beautiful, inverse, or exponential with negative growth. And then a nice visual there for us. Yeah, so that's Boyle's law. All right, then Charles' law. So they're choosing to present it with the cross multiplying. I think that's easier. I like this form more because I can just see without much thinking, these are directly related with positive sign. Gay-Lussac's, you don't have to ever know that that's what we call it. Pressure and temperature. And then my gas law. Again, don't have to memorize. No. But usually we see it as P1 V1 over T1 equals P2 V2 over T2. All right. Before we get to this, on the next page, I have written Avogadro. Okay. I know we all know what October 23rd is. Mole Day. Yeah? So October 23rd to celebrate Avogadro's number. But Avogadro played no role in determining 6.022 times 10 to the 23rd. He's known for his work with gases. Just after his death, we realized how correct he was. And so we chose, or they chose to name Avogadro's number. So, all right, Avogadro's law says this, that if you have two gases at the same temperature, pressure, and volume, they, or the gases, must contain the same number of particles, or we could say the same number of moles. When Avogadro presented this, he was laughed at. Because they said, that is just ridiculous. So, let's say carbon in the form of diamond. So if you have a sample of diamond, let's see, Michael, choose a volume of our. Oh, are we going to hold on to it? Or are we going to go ahead and make some money? All right. Let's appreciate it. Let's analyze it. But yeah, let's beef our bank accounts. So if we have 4 liters of solid, now solids really don't exert pressure, but let's say that the temperature is room temperature, let's just say. Well, what Avogadro is saying is, well, if we have diamond and the same volume temperature, again, like how can it exert pressure? So we're going to ignore that. Well, that would be the same as if I had 4 liters of liquid water at 25 degrees Celsius, that you would have the same number of molecules. And they're saying, that's just ridiculous. Ridiculous. Look at the density of diamond compared to the density of water. No way do you have the same number of particles. That's just silly. But it's true with gases and only gases. So he was laughed at because we were just starting to understand the gaseous state of matter. So no way is that true with solids and with liquids, but it is with gases. The identity of a gas does not matter toward its pressure, toward its temperature, toward its volume, or toward its amount. That's what's so crazy and unique about gases, where the identity of a solid and liquid determines totally its properties. Reason is, gases really don't show particle attraction, where that's what makes the liquid and the solid state. Avogadro's law. All right. I want to definitely applaud Maddie, because your problem solving that the insight that you had, is that okay? Okay. Because can I tell you that, Maddie, for 24, no, it's not that one way is better than another way, as long as we're getting to the same place, yeah? So you were told in number 24 that you have 5 liters of a sample of gas at 9 atm, and then these are connected by a valve, nothing like that. And then you open the valve, what is the new total pressure? Me, who does chemistry every day, said, okay, so these 5 liters, when they have an opportunity, are going to take up this vessel and that vessel. So what I want to find, it starts out at 9 atm. Well, what will the pressure be at 15 liters? Well, then this gas is going to do the same. So I found what this gas pressure will be. And then we know total pressure equals the pressure of the first gas plus the pressure of the second gas. When gases are combined, they behave individually. They ignore each other. But can you share what you thought of? If we call that 1 and 2, yeah? How about that impressiveness? Look, me, your silly teacher, did it separate, but that's bad, and then added, where Maddie had the insight to do it all at once. Pretty amazing. But why I'm highlighting this, yes, to give you credit for great thinking and problem solving, but also to remind us of this. This is called Dalton's law of partial pressures. So I'm going to go back to that page that had Avogadro's. Okay, Dalton's law of partial pressure. You know that you never have to remember the title of these. That if you have multiple gases in a mixture, the total pressure is a result of the individual gas pressures added. And we could just go on and on. We called those partial pressures because they're part of the mixture. Part of the mixture. Okay. Your questions. All right. Damien, sir, could I loft a question your way? All right. So let's say, sir, that on your lab bench, we have 2 containers same volume, 3 liters. This contains helium, and this contains, let's say, argon. All right. They're held out at room temperature, which approximately 25 degrees Celsius. Okay. And we measure that this is exerting 5 atmospheres of pressure, and this is exerting 5 atmospheres of pressure. How do the moles of helium compare to the moles of argon? How do you know? So can we, make sure that we understand the connection? If they're at the same temperature, they have the same energy of motion. Yeah? If they're at the same volume, they have the same amount of space they're taking up. And the collisions with the walls is exerting the same force per unit area. So it doesn't matter that this is helium and this is argon. It matters that they have the same kinetic energy, the same amount of space, and the same resultive collisions. Then we know those are equal. Okay. So, Dylan, what if on your lab bench, sir, I have the same 3-liter containers, and I'm just going to tell you there's oxygen in here and there's hydrogen in here. Sorry, they seem like they're different. And same temperature. This is exerting a pressure of 5 atmospheres. This is exerting a pressure of 2 atmospheres. How do these compare? How do you know? You're right. Okay, so same kinetic energy, same volume. Are there collisions? The result of the collisions. Force per unit area, force per unit area. Oxygen either has more forceful or more frequent collisions. So what must be true? All right, no worries, no worries. So, baby Groot. Okay, toss it to someone to answer. Heads up. Oh. Because? So if one of these is different, so Dylan, temperature, volume, and pressure are the same. So then we know this has to be the same. But here, they're not the same pressure. So what must be different? How much you have. Okay, sir? Okay. Okay. You're the possessor and going to be the chooser in a moment. Yes, sir. Such a great question. Gases, super freaks, because you would think, like, well, don't we have to know it's oxygen? Don't we have to know it's hydrogen? They're different, 32 gram per mole, only 2 gram per mole. What? Mass only plays a role if we want to know speed of your gas. That's it. Because, Tyler, there is so much empty space. This would have more, yeah. There's so much empty space, and they have such high kinetic energy, they're not showing particle attraction, that their identity doesn't play a role except in the specific velocity that it has. Yeah, so that's what's bizarre about gases. where liquids and solids, their identity determines everything about them. Does that address what you need? Okay, but I'm going to show you something else. Okay, Critton. Do you perchance remember this equation? It's okay. Have you seen this before? PV equals nRT. All right, we know pressure, volume, temperature, mole, R. Do you recall capital R? And of course, we're seeing it here. R is called the gas law constant. Now, when we are employing R with gases, we use the value of 0.8206. You don't have to memorize this. I will give it always. But there is another value of R that every other chapter will employ that. So only with gases. And there's a couple values of R depending upon what the pressure is expressed in, but we're going to be in atmospheres mostly. So let's just rely on that version. You don't have to write this down, but just to let us know, R also has the value of 8.314 joule per Kelvin mole. You can use this, even though it's still called the gas constant, with solids and liquids. Weird. And this brings in the unit of energy. So that is why, but that will be to come. All right. So here's your question, sir. You may answer or you may volley it to someone else. So could we, amazing students, turn a couple pages until you're on the page that reads ideal gas law? Okay, so Critton, what is our equation again, please? It has a ring to it, I think. PV equals nRT. All right. Pressure, volume, temperature, moles. You don't have to memorize it. I will give it 0.08206 liter, atmosphere, Kelvin, mole. Okay. Now, I know none of you now or when you were, yes, sir. I'm sorry? It's definitely 0.08. NIMSY. Double check. Yeah. My friend Renee McCormick made these. She made it. Thank you for catching that. I promise. Yeah, I promise. Oh, sure. I don't think. I promise, sir. I don't know if you want proof at this moment in time. Promise. Yeah. Okay, but that all right. Anyway. Okay, Critton, here's your question. Oh, we do not get overwhelmed with this. The poor honors kiddos, when they first see this, they're like, like it's a different planet. Nope. Critton, this combination of units serves to deliver whatever we're solving for, the unit for that. Okay. Knowing the value of R, what unit does pressure have to be in for the ideal gas law? Oh my gosh, yeah. Has to be. What about volume? Yeah, has to be. You don't have to memorize this. I will give this. So just look at this to remind you, oh, we know temperature has to be in Kelvin. And then moles are moles. Yeah. All right. Could you help with the next one. So can you please read this problem? Okay, so I'm given a volume, I'm given a temperature, I'm given a pressure, and then we're asked for mass. We're not given an initial volume and a final volume, initial temperature, final temperature. So PV equals nRT. And Critton, what would you solve for? Ah, okay. In AP chemistry, we can use V1 P1 equals V2 P2. We can use V1 over T1 equals V2 over T2. We absolutely can. But the attitude and the approach is this. We call it the ideal gas law, of course, because ideal gases perfectly obey these relationships. But it is the golden equation to deal with gases. When we are preparing for the exam in May, when you know the problem involves gases, we should bring this equation to mind. That is the one we employ most often. So just to illustrate that we really, we don't need these. Okay, suppose we have a volume of ammonia with a volume of 7 mils at a pressure of 1.68 atm. Never ask you to write down givens. I'm just going to for the sake of illustration here. All right, the gas is compressed. So my next volume is 2.7 milliliters at constant temperature. Use the ideal gas law to calculate the final pressure. Use the ideal gas law. So I have this first volume and first pressure and first volume. Okay, I have P2 and V2. We know that R is constant. You're at the same temperature. It says nothing about changing the amount. So P1 V1 equals P2 V2. So we can derive all the other gas laws from the ideal gas law. But you can go right to this. Okay, you can go right to that. It is actually 4. I'll just let us know if you're solving it. 4.4 atm. And it just takes a moment. Go ahead and toss it to someone. just takes a moment to check the reasonableness of the answer. So Isaac, from the first to the second condition, what do we do with volume? When you decrease volume, what is the expectation of pressure? Exactly. And did we? Yeah. A reasonable amount? Yes. Okay, good. So I've just shown another example deriving from the ideal gas law. All right. Let me look at just one more thing and then we're set. Just one more thing. Easy, easy. Okay, Isaac, do you want to answer or toss it? Okay, molar mass. I will always represent molar mass with capital M, capital M, because I don't want to be confused with molarity. Know that Zumdahl often just uses a capital M. I will always use MM, and you can use MM for it. So, Isaac, what are the units we know molar mass will have? Yeah. Take that to the bank all day long. So, could we say the equation for molar mass would be mass divided by mole M over N? Do you want to answer or toss it? Okay. Density. You could use a capital D, but usually lowercase d. What is the equation for density, sir? We know, right? Gram. Now, with gases, we usually need a big volume to have a workable value for mass. Otherwise, it'll be 0.00 grams if we do grams per milliliter. Okay, a reminder of this and a reminder of those will play a key role tomorrow. Okay. Damien, something that you were reminded of today that you had forgotten about gases or something you learned?